Okay, we already know how to write any Boolean function using only the operators and, or, and not, which in predicate logic go like this. And this means that this set of operators is functionally complete, right? So if we have any expression in predicate logic, no matter how complicated it is, we can always rewrite it using only those. Now, we could then ask, is this the only set of operators that has this property? Are there other sets that that are enough to write any expression in predicate logic? And also, are those three necessary? If I make this set smaller, can I still write any function? Could I write any function, for example, using only and or? Well, it turns out that with and or, no. If you drop the not, you're not able anymore to write any Boolean function you want. We can quickly give an argument for that. Notice that both and or are commutative, right? Meaning that they have exactly the same result if you reverse variables, right? And this is not true, however, of any Boolean operator or any Boolean function, right? You could easily have a very simple Boolean function like implication, which is not commutative, right? So, what this means is, no matter how I combine those operators, those two here, I'm going to get some result that is commutative, clearly, right? Because if I start just combining them, I don't know, P and Q, or Q and P, or Q, if I'm only using ands and ors, however I combine them, I'm combining operators that are individually commutative, so the result itself, if I switch P and Q, will not change. This means immediately that I can never hope to write P implies Q using only ands and ors, because this is not commutative. And whatever I write using only ands and not will be, ands and ors will be commutative, right? So ands and ors, no, they are not functionally complete. You can't write every Boolean function using ands and ors. In particular, you can't write implication. Right? You can write implication if you use the not, and we already did it, right? And it's very simple. The P implies Q. One way to write it, it would be simply not P or Q, right? And if you don't see this immediately or don't remember it, you can just look at the truth table for P implies Q, which is essentially true everywhere except on this line. Oops, I'm doing the function already. P implies Q is 1 everywhere except here on line 2, right? So if you write this thing in CNF, how do we write the truth table in a CNF expression in predicate logic? Well, we'll look at the zeros. In this case, there's only one zero, and then we write an OR term for each row that is zero. In this case, there's only one row, and then we write the negation of the value of P here, or the negation of the value of Q here. So we have not P or Q. Okay, so this represents this truth table, which is the truth table for p-implied q. That's one way you could do it. So we were just able to write an expression using only those operators for p implies q. So those three are functionally complete. Ands and ors alone are not. How about some other subset? Instead of dropping the not, maybe I could drop, say, the or. Can I write any expression in predicate logic using only ands and nots? Maybe I can, right? So let's see if this is the case. Well, I'm already going to spoil the surprise and answer the question. It is the